Okay, so this is a return to problem 30, where I kind of dropped the ball here on why it is we choose to take the derivative and do all these things to find the range of iteration. So I've got a bit of a deeper explanation here. So why don't we just cancel D? Well, I mean, basically I was lazy about that equals sign between the two halves. So it's more like we're like, what is the relationship between these two? Because as we will explore, just canceling out the d's is not quite as straightforward as we thought, right? So really what we're doing is we're saying the left-hand side is this particular function and the right-hand side is this particular function. And then we take the derivative of both sides once again. So this is the left-hand side, we take the derivative, and we set that equal to a constant lambda. And we do the same to the right-hand side. We take the derivative, and this includes the partial sum result, and then we set it equal to lambda and constant. And then why do we do that? So it's a way of connecting the two relationships, the two functions. And it sort of scales them and balances them automatically. It's sort of like a simplified result. It's a heuristic result that is found through something called the calculus of variations. So there's a whole field of study about these interesting shortcuts that you can find with calculus for to apply to functions and get relationships between things in a form that sort of optimizes under your conditions. So the conditions that we picked earlier based on the problem are what determined how we set each side of the equation, and then take the derivative, set those to constants, and rework and solve for D. So you can see here on the right we've got a plot of D versus X. So X is the number of digits on the bottom, and D is the average digit value. And so once the average digit value is a 9, you can't go any higher. So that's as high as you can go, right? When X digits are all 9s, right? So that's what this yellow line represents, is like this is all 9s. And you can see it just shy of 5 digits. So we know that the range was going to stop between 5 and 6 digits. And so we can kind of plug it in. We can say 9 for the left-hand side, right? Basically, y is equal to 9, right? Set that equal there. Rearrange and solve for x. Now this monstrosity is precisely why I wasn't trying to rearrange and solve for x in terms of D earlier, because I knew I was going to do something terrible like that. This W function is dirty to play with. So I didn't do that because it would not have made things easier by any means. But as you can see, this is pretty much what we expected. If we were to take this number and kind of work backwards, we'd find that it would spit out the approximately 300,000 upper bound that we'd expect. So that's just the sort of slightly longer, but still not quite long enough explanation for why we did that operation with that at that particular moment. All right, thanks. Have a good one.